Curve C, shown in figure 4, has parametric equations x equals 1 plus root 3 tan theta and y equals 5 sec theta, where theta is between minus pi over 2 and pi over 2. The curve C crosses the y-axis at point A and has a minimum turning point at point B, shown in figure 4. Find the exact coordinates of A. So point A, that's where it intersects on the y-axis, so I know that is where x equals 0. So let me take the x parametric equation now and make the x equal to 0. And we'll rearrange that. So take the 1 away. Divide both sides by root 3. And if I do tan inverse of the minus 1 over root 3, I get minus pi over 6, which is in the range of thetas allowed, so that's fine. That is my value of theta. So to work out the exact coordinates of A, like I said, I know the x coordinate is 0. I now need to know the y coordinate. So I want to substitute the minus pi over 6 in here. Obviously, I can't substitute that directly into sec, but I can substitute it into cos. So I'm going to rewrite the 5 sec theta as 5 over cos theta. So substituting the minus pi over 6 in here. So 5 divided by cos of minus pi over 6 gives 10 root 3 over 3. So that is the exact coordinates of point A. Part B. Show that dy by dx is lambda sine theta, given the exact value of the constant lambda. So dy by dx, our gradient function. In terms of parametric equations, I can use the formula dy by d theta divided by dx by d theta. Differentiating my x equation, the 1 will differentiate to be 0. The root 3 tan theta will differentiate to be root 3 sec squared theta. Now to differentiate the y function, we've got 5 sec theta, which is going to differentiate to be 5 sec theta tan theta. Sec differentiates to be sec theta tan theta. That is on your formula sheet, so you can look at the formula sheet to check that. Substituting those into our gradient function then, we've got 5 sec theta tan theta over root 3 sec squared theta. And I just need to try and show that that's going to simplify to be lambda sine theta. Well, we can see that the sec thetas are going to cancel out. So let's do that to begin with. So that's going to leave us with tan theta over sec theta. Now, the tan theta, I know that's the same thing as sine theta over cos theta. Then I've got the 1 over sec theta. I'm dividing by sec theta here. So dividing by sec theta, well, let me write it as time. Let me write it like that. And the 1 over sec theta, that's just cos theta. Which is then going to cancel the cos theta there. So I get 5 over root 3 sine theta. And that's what I needed to show. So lambda is 5 over root 3. Part C. Find the coordinates of B. let's remind ourselves, B was the minimum turning point. So that's where our dy by dx is equal to 0. We've just shown that dy by dx is this. So when does 5 over root 3 sine theta equal 0? Well, it doesn't matter about the 5 root 3. Sine theta has to equal 0. So therefore, doing sine inverse on both sides, I find that theta would have to equal 0. Substituting that into my x and y equations here. So x equals 1 plus root 3 times tan 0 is just 1. Y equals 5 over cos theta, or cos 0, is 5 over 1, which is 5. So the coordinates of B are 1, 5. Finally, part D. Show that the Cartesian equation for the curve C can be written in the form y equals k times the square root of x squared minus 2x plus 4, where k is a simplified surd to be found. So Cartesian equation, so I want to find a way of getting only y and x here, so I need an identity linking the tan theta and the sec theta. Well, the obvious identity for me here is that 1 plus tan squared theta is equal to sec squared theta. That's the main identity I think about when I think about tan and sec theta. So if I make tan theta the subject of the x formula, so I'll take with the 1 away, and then divide by root 3. I can then substitute this in here. Similarly, if I make sec theta the subject here, so sec theta is equal to y divided by 5, and I can substitute that in here. So let's do that. We would have the 1 plus the x minus 1 over root 3, that's my tan squared, equals the sec, which is the y over 5 squared. Right, let's carry on from here, and I just need to try and make this look like this now. That's my job. I've got a Cartesian equation, I just need to make it look a bit simpler. So first of all, let's do the squaring. So x minus 1 all squared. So x minus 1 all squared over root 3 squared, which is just 3. Then I've got a y squared over 25. Next, let me multiply both sides by 25 here to get rid of that 25 fraction. So 25 times 1 is 25, and then I've got 25 lots of the x minus 1 all squared over 3. Next, whilst I'm at it, let me get a common denominator on the left-hand side. So let me times here by 3. So that's going to give me 75 plus, right, 25 lots of, let's expand this bracket here now. So I'm going to get x squared minus 2x plus 1. Let's tidy this up, so expand that bracket. 25 lots of the x squared. Then I've got 25 lots of the minus 2x plus 25. Collect up like terms. Now I notice that 25 goes into each of these. I can factorise 25 outside. And I can see that I'm nearly here now. You can see I've got the x squared minus 2x plus 4, which I have here. All I need to do now is to square root both sides. So square root here, square root here. So I get y equals, now the square root of 25 is 5. I can't square root the 3, so I'll leave that as root 3. And then I will have the square root of x squared minus 2x plus 4. So I have y in the form that it asked for. This is in the form that it's asked for. I can probably simplify this third a little bit more though. So let me rationalise that denominator. So 5 over root 3 is the same thing as 5 root 3 over 3. So that would have been a better way of me writing that. And there we go.